At this point, let us do GUI underscore show. So it has so it will show the schematic at this point in time. So all you have to do is you have to click on the plus, and then you can add the schematic or the HDL viewer. You can also view the HDL viewer here. But it's usually a good idea to view the schematic at this point in time. So here notice that there is a flop here. So like I said, SynGen is going to map it to a generic set of gates. It's called, it just knows that it's a flop here, it's a NOT gate here. It's not yet mapped to the technology file yet. So at this point, you can hide the GUI. So it's going to be a little slow if you're accessing it from VPN. So you can also minimize the schematic. Then let us do syn map. So it now maps everything to the, it's quite fast. So it is done before you actually hit it. So you can see that it has mapped it to the technology file. And the way to know that is if you go back to the GUI show, you can view the schematic now. You actually have to do GUI show again to view that particular new schematic. Let us see if this works. So now also it is showing it's a flop, but if you actually move the cursor over it, it will actually tell you what lib cell it is. I should have ideally shown this before we did the last step. Maybe we can, let me just repeat all the steps at this till this point and then show you the difference. Yeah, so I have actually rerun I have exit genus, and then I have opened it again, and then I've typed in all the commands up till syngen, and then I've done GUI show. At this point, uh, if I move the mouse over the flop, it just shows that it is an instance of count reg6. It exactly doesn't show me what is the library cell it's been mapped to. Similarly, if you move over the inverter, it's going to tell it's the instance G1 and so on. So at this point, it is not showing us that it is mapped to any cell or any library cell. So let us at this point, let us do the syn map. And let us now go back to this and view the schematic again. So at this point, if you move the cursor over this instance, it's going to show that it's mapped to a particular lib cell. So we can at this point do report gates. So it's going to tell us what are the gates that it has used. So it's going to print everything out on this console here, but you can also redirect it using this redirection to a file. So it's saying that it has used a few adders, inverters, NAND gates, OR gates. It tells you how many of them it has used here, what is the total area that it has consumed, and what is the library that it has used, a total number of instances, and total percentage of area that it has used. So once you do that, we can now do synopt, which is optimizing the design. It is going to incrementally optimize it. Is if it does not meet, for example, the timing, it is going to reiterate over it again and again. At this point also, it's a good idea to check report underscore gates. You can now see that the number of gates has come down from earlier it was 23, now it's 21. So now we are done with all the synthesis steps. We can just write out all the files that you want and just copy paste all of this here, and you should be able to see all the reports in this new results folder. So we have synthesis reports and new results, and you should be able to see the HDL synthesis. HDL underscore synthesis is the Verilog file, and you should be able to view the synthesized netlist here. So basically this is nothing but structural code which has been created by the tool with the help of these inbuilt gates, the inbuilt gates from the library file. So you can simulate this file. You should be able to see the same output from the counter. And for that, you need the descriptions of these gates. So you should, I'll have to uh, figure out where the description of these gates are, but it should be in one of these library files that has been provided along with the PDK. So that is one of the outputs that we need. And then we can also check the area here. So this is the total number of cells. And then you can also check out the timing. So currently it is showing the timing for this slow library with these operating conditions. And it's showing only one path. And the path is starting from count reg 0 clock to count reg 6. So this is, I guess, is the critical path, which is the longest path. It's showing just one path right now. So we can also report multiple paths and we'll do that later. So it is showing what is the path starting from this count reg 0, what are the different gates through which it is going, and what is the fan out of each of them, what is the delay created due to each of those gates, and this is the arrival time, the rising and the falling, and so on. So basically we said we want to meet a 1 nanosecond, so this is 1000 picoseconds, and it says that the path has met the timing with the slack of positive 51 picoseconds. So this is an important parameter for us to understand. Then it also has this counter STC. So it is created, it's created by the tool. If it has done any modifications to the delays, etc., it is going to put it out here.